All right. So first of all, sorry about the delay. Fortunately, the my pen died, so it was going to be very hard to show you guys how to do this without the pen working. But I've got one working now, so hopefully this will go smoothly. And just a couple of things. So today, homework 7 is due tonight. Um, And this will, I am going to go over homework 8 unless anyone has any objections. Uh, this one will be due next Wednesday, as long as nothing kind of, messes with that. Um, yeah, my plan is just go over homework 8. If you have any questions on homework 7, feel free to let me know. I'll try and cover them as best I can. Feel free to interrupt with any questions, but I'm just going to go ahead and get started. All right. So this is a shorter homework. Problem 1. So we're given this mechanism for creating tert-butyl alcohol, or TBA. And it is a catalyzed reaction. And we want to find the rate law for the disappearance of I by using the assumptions in parts A and D. So we want minus RI. So I guess we just want RI. So that will be the disappearance. For the sake of this problem, we can assume that theta I for all steps is equal to 1. And we will move on. Okay, so part A. Part A assumes that the surface reaction is the rate limiting step, and we assume all other steps to be QE. So, in this case, the surface reaction, the step that's actually giving us the TBA, that is step 3. I guess step 3. So we can say that R3 is equal to RI. All right. And using what we know, this thing will work. There we go. Looking just at the reaction itself, we can write out the expression based on what we have. So we have the forward reaction times the concentration of WS times the concentration of IS minus the reverse reaction times S. And remember, because each side has 2 surface species, we need to divide by CT on both sides. If we had 1 surface species, we wouldn't have to divide. If we had 3, we would have to divide by CT squared. But since we have 2, we divide by 1 CT. Okay, and if you remember from homework 7, we cannot have any of the surface species or empty sites in the final rate expression. Cannot have any S, IS, AS, and S. And unfortunately for this problem, that's all we have. So now we gotta work on getting rid of those. Okay, so in the problem statement, it says we can assume all other steps are QE. So starting with reaction 1, the first step, R1, we can say that the forward reaction, which is K1 times nope, make sure I get this right. There we go. is equal to the reverse reaction. Why is R3 equal to Ri? So we're ultimately trying to find the rate of disappearance of I. So that would just be Ri. And based off of the fact that we've said all sigmas are equal to 1, we can also say that R is equal to Ri over theta. Oh no, sorry. That's wrong. But the overall, if we're assuming that all of them are equal to 1, then we'll get our reaction is equal to I plus W goes to TBA. And because the stoichiometric coefficient of I is just 1, we can say that R is equal to Ri over nu I, which is equal to R1 over minus 1. So R is equal to negative Ri. And we said that the rate limiting step, the rate, is R3. So that makes R equal to R3. So by that logic, R3 will be equal to Ri. So from there, going back to the expression for step 1, we can find our surface species to be capital K1 times I times S. Zoom in. So there's one species accounted for. We can do the same thing for step 2, where we say that K2 times W times S is equal to K minus 2 times WS. Again, this is just because we are told that we can assume all steps, aside from step 3, are QE. Oh, Lord. There we go. So from there, WS is equal to capital K2 times W times S. All right, there's the second one. Now we have to do the TBA. We can do that from step 4. So we've got up. I can actually see it. There we go. So we have that K4 times TBA S is equal to K minus 4 times TBA times S. And we will get that TBA times S is equal to TBA times S over capital K4. All right, so that takes care of that. But we are still missing an expression for S, and S is going to come in with the our total site balance, CT. So CT is just the sum of all either occupied or empty sites. So we have our empty sites in S, sites occupied by I dot S, sites occupied by W, and sites occupied by the TBA. All right, now plugging in all the expressions that we've solved so far to get this, we're going to get that CT is equal to K1 just make sure I did that right. All right, that looks good. Okay, so now we can take an S out of every term and solve for it. We get that concentration of S is equal to Ct over 1 plus capital K1 times I. Oh man. Plus capital K2 times W plus TBA over capital K4. So there's our expression for the for S. So that covers all of the unknowns that we can't, or I guess all of the the concentrations that we can't ultimately leave in our reaction rate, our rate expression. So going forward and plugging everything in, this is going to be a lot. We're going to get that K3 capital, oops. Forgetting. Okay, and all I did right there was just plug in these three expressions. So now all that's left is plugging in our expression for S. And that is going to end up looking something like, I'm going to cheat. And that is your expression for there should be your expression for the for part A. Can we discuss parts C and D at some point? Yes. I'll probably just end up going through the whole assignment, so I'll definitely be able to get 2 parts, number 2, part C and D. Oh, are you asking about 2 parts C and D on homework 7? If I'm remembering, there is no part C and D on this homework too. On number 2 for this homework. Oh, and I forgot a little side note because I was trying to make sure that my answer made sense. So we actually know that we have this notation right here. So the actual rate expression, almost the same. We just don't want to have any of that capital K4 in there. So, because we can say that 1 over capital K4 can simplify to capital K TBA. Trevor is due tonight. My goal seek isn't really working. Okay, that's homework 7. Yeah, I will go through this one. This one isn't, homework 8 isn't too terribly long, and then I can go and help you out with that. As long as I stop making mistakes. And that's probably a better expression for part A on number 1. So yeah, long, complicated, but it's not too terrible. Can you scroll back up to the QE for step 4? I think I copied it down wrong. I don't have a K4 on the bottom anywhere. Okay, so here's the one for step 4. And remember that I'm solving for this, my surface species, the TBA times S. So I have a K negative 4 over K4, which is actually 1 over K over 4. But I forgot the substitution that he gave us. So this will technically be equal to capital K TBA times TBA times S. Because remember that it was given in the problem statement that K TBA is equal to K minus 4 over K4, which is also equal to 1 over capital K4. So that's where that substitution comes in. All right, so if no more questions on part A, I'll move on to part B. If I can zoom out to show it, whatever. All right, so the absorption of isobutane is rate limiting. All other steps are QE. Isobutane is I, so that's going to make our first step our rate limiting step. And all other steps are QE. So, based off that, if my computer will load, there we go. So R is going to be equal to R1, which is now going to be equal to K1 times I times S minus K minus 1 times IS. Notice each term only has one surface species, so there is no need to divide by CT. So, what are the terms we need to get rid of? It is our S and the I dot S term. So, in getting rid of I dot S, remember we can assume QE on all steps. So if you remember back to R2, since nothing has really changed with that one, that's the wrong species. W, oh good lord, W dot S is still going to be equal to capital K2 times W times S. And remember, that's just assuming QE on step 2. From R4, we can still assume that TBA dot S will still be equal to capital K TBA times TBA times S. But now we have to assume QE on step 3 in order to get an expression for I dot S. So that's going to give us, so we'll have K3 times I dot S times W dot S is equal to K minus 3 times TBA dot S times S. Make sure I did that. Yes, that's the reaction for step 4. All right, solving for I dot S, we are going to get is equal to TBA dot S times S over capital K3 times W dot S. And plugging in our expressions for TBA and WS, we get that I dot S is equal to squared over capital K3, capital K2. And then we can cancel out one S from the top and bottom, and that gives us our expression for I dot S. So going back into the overall rate, R is equal to K1 times I times S minus K minus lowercase k, if I can get that, K minus 1 times K TBA times TBA times S over capital K3, capital K2 times W. All right. What terms do we have to account for now? We have to get rid of these S terms, and we'll do that using a site balance. So very, very similar to part A. We're just by switching what is the rate limiting step, that's going to ultimately change our rate. So same as before, we account for all of them, occupied or unoccupied. And plugging in our expressions. Make sure I get these right. Okay. is all equal to CT. And then going back and solving for our concentration of S, we get that CT equal to 1 plus Q3 Oh, man. All right. So now we can plug that back into our rate expression. So we'll get R is equal to times K1 times I minus K minus 1 times capital K TBA times TBA over capital K3 times capital K2 times W. All right, and that's that for part B. Again, not too terrible, just kind of wash, rinse, and repeat what you've already done. All right, so moving on to part C. Those are no questions. So part C, we are given, it's the same reaction, but we are now following a new set of kinetics. So we are now dealing with a much shorter, a much smaller reaction where our W doesn't need to be bonded to the catalyst in order for it to react. And we are told that the surface reaction is rate limiting, so the step that's actually producing our TBA is rate limiting. In that case, that is this one, step 2. Again, we'll make the same assumptions that theta I for all is equal to 1. So, because we know that the surface reaction is rate limiting, we know that R equals R2. The reaction, there we go. Which is equal to K2 times IS times W minus K minus 2 times TBA times S. All right, so same as before, we can assume QE on all other steps. So we see that we need to get new expressions for these surface species terms. So from rate 1, assuming QE, we get K1 I S equal to K minus 1 I dot S, making I dot S equal to capital K1 times I times S. So about the same as before. From R3, we have that K3 times TBA dot S is equal to K minus 3 times TBA times S. That makes our surface species equal to, there we go, over capital, I guess, let's do it this way, so it's a little clearer. We have K minus 3 TBA times S over K3. From the problem statement, we're told that K minus 3 over K3 is equal to our capital K TBA. So making that substitution, that is our expression for our surface species of TBA. All right, plugging those in, we get R is equal to K2 times capital K1 times I times W times S. K2, or sorry, K negative 2 is equal to capital K TBA times TBA times S. All right, and once again, we have the our concentration of S, our concentration of the empty sites. So we got to do a site balance in order to get rid of those, that term. I dot S. Ooh. So plugging that in, we get CT is equal to concentration of S plus capital K1 oops, nope, it's not W, sorry. Force of habit. We don't have water bonding to any of our sites, so we don't have to worry about that term. And solving for S, if I can write it properly, sorry about my hand, capital K1 times I plus capital K TBA times TBA. All right, now we can go plug that back into our rate expression and we will get and there you go. Nice and easy. Well, really with this problem, if you're able to do problem 1, or part 1, part A, the rest of the problem is really following the same method. So, it's just a great way of practicing mechanisms. So, moving on to part D. What is part D? If I can go. There we go. Okay, isobutene and water are absorbed onto different sites. The surface reaction is rate limiting, and TBA is not on the surface. Assume all other steps are QE. There is no need to divide by the total number of sites in this rate expression for this part. Okay, so once again, we can assume that for all is equal to 1. Our third step is rate limiting. But now we have two different sites. We have an S1 and an S2. And that is going to, that will change slightly how our rate expression will look. So if I can get it, there we go. So based off that, R is equal to R3, which is equal to K3 times I dot S1 times W dot S2 minus K minus 3 times TBA times S1 times S2. And under normal circumstances, because as you see on both terms that we have at least two surface species, we would have to divide by CT. But he mentions in the problem statement that there's no need to divide by the total number of sites in the rate expression. And the reason for that is there are two different types of surface sites. So dividing by CT kind of accounts for this probability of one species being on a surface over another. But in this case, we only have one species on one type of surface. So in this case, we only have I on surface 1. If, let's say, we had W times surface 1, then we should divide by the total number of sites. But we only have one species on one site. So that's kind of the same thing as saying we only have one term, kind of how we had it up, in part C. So because they're different, there's no need to divide by that. Excuse me. Okay. But we still can't leave these terms in the rate expression, so we have to go and get rid of them. So once again, we can assume QE. So on the step 1, we have K1 times I S1 of I is equal to K minus 1 times I dot S1, which gives us I dot S1 is equal to capital K1 times I times S1. Same thing on step 2. Okay. And that's just from our QE assumptions. So now we get that for plugging those terms back in. All right, and we still have our empty sites, the S1 and S2, so we'll have to do a site balance to get rid of those. However, since these are different types of sites, we have to do different site balance for each one. So we'll actually have to do two site balances. So we'll have to do a CT1, and then we'll do a CT2. So CT1, kind of the same way we've always done it. Where we have the empty ones and everything that's bonded to this site. And as we mentioned before, only one species is bonded to this site, and it's going to be the isobutene, I think, that I.S1. So that's going to be equal to S1 plus capital K1 times I times S1. Solving for S1, we get that is equal to CT over 1 plus capital K1 times I. And then same thing for CT2. We have our empty sites of site 2 plus all of our species bonded to site 2, in this case only the water. I believe it's water. It is. Okay. So it's going to look very similar to the one we just did. So now we just go and plug those in. Oops, and make sure it's clear which site balance is which. So we will end up with R is equal to K3 times capital K1 times capital K2 times I times W times CT1 times CT2 over 1 plus capital K1 times I, 1 plus capital K2 times W minus K minus 3 times TVA times CT1 times CT2 over the same denominator as before. Oops. And there you go. Part D. So I think the main focus of these problems, with this problem, is, of course, understanding the mechanism, understanding QE and where you can apply it, and understanding the actual site balance, and knowing that you can't leave these terms, your empty sites or occupied sites, in there, but you can leave the total number of sites in there. And by doing a site balance, that helps you. That's one way of helping to get rid of these terms. All right. So if there aren't any other questions on this one, I will move on to number 2, which is slightly more involved. Drink. All right, problem 2. So the irreversible gas phase reaction A goes to B is carried out in an isobaric PBr packed with catalyst particles. The reaction is first order in the concentration of A on the catalyst surface. The feed consists of 50 mole percent A and 50 mole percent inert and enters the reactor at a temperature of 300 Kelvin. The entering volumetric flow rate is 10 liters per second. The relationship between the Sherwood number and the Reynolds number is that. And we know that the entering concentration, or Ca0, is 1 molar. So, and also important on this one, assume that the reaction is externally mass transfer limited. Okay, so part A, we're going to operate this reactor isothermally and we need to find the catalyst weight necessary for 60% conversion of A. Okay, so there was a lot there. So, I guess where to start. And in this case, we are operating the reactor isothermally, so there is no need for an energy balance. So we can just jump straight to the mass balance, and usually with these kind of reactors, the mass balance is the design equation. And for those of you that don't remember the design equation for a PBR, I would become more in tune with it. I guess it'll just be W is equal to FA naught times 0 to XA dXA over minus RA prime. And is very similar to the PFR, except we are not finding the volume, but we're instead finding the weight of the catalyst, and we're using the minus RA prime rather than minus RA. Okay, so plugging in what we have for minus RA prime, we have FA naught dXA over K prime times CAS, where CAS is the concentration on the surface. But we don't want to leave this in terms of the concentration on the surface, because it's much easier for us to solve for this is when we know the concentration in the bulk. So we don't want it in terms of CAS, we want it in terms of CA instead. So how can we get it in terms of CA? Remember that in the problem it mentioned that it is externally what did it say? External mass transfer limited. That's it. And when we are assuming that it is mass transfer limited, we can write the flux WA to be like this. We have KC times CA minus CAS. And that was in the slides. And also, because we are assuming that this is at steady state, we can also say that our flux is equal to our surface reaction. Surface reaction. And our surface reaction, we are told, given in the problem statement, is just minus RA prime. Yep, just that. On the catalyst surface. Or RAS prime, sorry. So that is equal to K prime times CAS. So plugging that in, we have K prime times CAS is equal to KC times CA minus CAS. And from here, we can solve for CAS fairly easily. So we'll end up with CAS is equal to KC. We're using so many primes. KC times, oh man, let me go back to it. There we go. CA over KC plus K prime. All right, so now we have an expression for CAS. Do we know KC? We don't. So, if you'll also from the slides, let me find it. There we go. Using dimensionless quantities, we have that the Sherwood number is equal to Kc times dP, which is the diameter of our particles, over dAB, the diffusivity. From there, so we can rearrange that to give us Kc is equal to dAB times the Sherwood number. over dp. And we're given an expression for our Sherwood number in terms of the Reynolds number is, let me go back and find it. There we go. Times 100 times the square root of the Reynolds number. That better. Over dp. And that substitution was just made from what was given. Oh, and I forgot to mention up here that while this is true, we're not actually working with Kc. We're working with a Kc prime, which normal Kc is just is on a volume basis, but we're going to be working with a Kc prime because we are we're working with a catalyzed reaction, so we'll have to operate in a mass basis. So we'll have a Kc. So we ultimately want to find Kc prime. And when you go through this, you're actually only going to get Kc. So from there, we need to get from Kc to Kc prime. So this is how you can get Kc. And if you'll remember, the Reynolds number is equal to rho Vd over mu. Or substituting in for the kinematic viscosity, we'll have Vd over nu. Let's say find the Reynolds number, and how now we need to get Kc prime from Kc. I can find it, there we go. So Kc prime is equal to Kc times the times alpha, where alpha is the catalyst surface area per mass of catalyst bed. And it should be in units of, and for this particular problem, it's given in units of centimeters squared per gram of catalyst. Is that d the same as the particle diameter in the from the Reynolds number? Let me check. Excuse me. Let me look at my solutions. It is. For this problem, it is. So, let's write for this, dp is equal to d. I don't think you're given any other diameters. Nope. Yep. So that is a particle Reynolds number, so it is based off of the diameter of that particle. Okay. So for this problem, alpha is given. And right here. So once you go and find Kc based off of your diffusivity, Reynolds number, and particle diameter, you can multiply that by that alpha to get Kc prime, which is actually what you're going to want to use. So great, we now have Kc prime. We have an expression for CAS, and so for CAS, and I'm just going to substitute in the initial concentration and the conversion, because remember our integral is going to be in terms of conversion. Prime. So now we can plug all of these in to our design equation. So we have FA naught times 0 to XA dxa over k prime times, and then our expression for CAS. CA naught, oops, make sure I get everything. K prime C, CA naught times 1 minus XA over K prime C plus K prime. Which is equal to our catalyst weight. And a lot of stuff here, but if you remember, because we're doing this isothermally, we can take a lot of stuff out. So FA naught obviously can stay out, and then we multiply by KC prime plus K prime over K prime times KC prime times CA naught. Between 0 and 0.6, because that is the conversion that we are operating at, that we want to know our catalyst weight for, over 1 minus XA. So, as you can see, we can take out quite a bit, because we're operating isothermally, that all these K's will stay constant. And then that is a relatively easy integral to do, and that's kind of where I'm just going to leave you guys with that. You know, we are given CA naught. I believe we are given K prime. Yes, we are. We're given it at the temperature that it's operating at. I showed you how to find KC prime, and you can find FA naught from the values that you're given. So I'll leave you with that, as long as there aren't any questions on that part. Let's box that. Okay, and part B. Part B, if the reaction is operating adiabatically, what is the catalyst weight necessary for conversion of 60% conversion of A? Okay, so essentially the same thing, but now it's adiabatic rather than isothermal. So from there, we got to see what changes. So our expression for K is still going to hold true. Oh, maybe I didn't make it too clear, but this is technically, for CA, this is technically a gas phase reaction. So I should have showed the whole expression on how we get there. One plus epsilon XA times, I believe, T naught over T times P over P naught. So operating isobarically, that goes to 1. In this case, for part A, we're operating isothermally. That also goes to 1. Epsilon is equal to delta times YA naught. YA naught is equal to 0.5 because of the inert that we have coming in. Delta, in this case, is equal to 0, because if we remember, the reaction is A goes to B, 1A goes to 1B, so it's going to just be 1 minus 1 is equal to 0. So that whole term on the bottom will then go to 1. So that's why CA can just be simply written, even though it's a gas phase, CA naught times 1 minus XA. So it works out nicely. For part B, it's almost the same. So once again, we have the CA naught 1 minus XA. Epsilon will still keep going to 0. P over P naught will still go to 1. But we now have to consider our temperature change, T naught over T. So there's our expression for CA. Our expression for CAS remains the same. KC prime times CA over, let's make sure I'm writing this right. There we go. Kc prime plus K prime. Our method for finding Kc prime will also stay the same. Since Kc is a function of your catalyst, but K prime, which is the actual kind of reaction, the reaction constant, that is going to be a function of T. It's going to be a function of T based on the Arrhenius equation. So, using that, we'll get that K is a function of temperature in the following method. 1/T. And we are given K prime at 300 Kelvin. The react from the mass balance, the design equation will stay essentially the same. dxa over minus Ra prime. And for the most part, all the work we did up here can still apply. So we'll still end up with Fa naught times Xa over K prime times Kc prime times Ca over Kc prime plus K prime. That's all still fine and dandy. Are we given the activation energy? I think so. Let me. Yes, right there at the very bottom. Okay, and excuse me. So there's our mass balance, and then once again we're working with a non-isothermal system, an adiabatic system. So we have to do an energy balance. So starting from there, write out the whole thing. Q dot minus W dot S minus A naught delta HR XA T minus T naught. Let me move everything down. I'm crowding myself. I don't like that. I don't know why I did that either. It's been a long day. It's been a long week. That's okay. Okay. So I write the energy balance. So we are almost always operating at steady state. We have no shaft work. And since we are adiabatic, Q is also equal to 0. For this problem, we are given the heat of reaction at just, we can find that delta Cp is going to be equal to 0, which means that delta HR of T is not a function of temperature. All right, I guess it's misleading to say that is not a function of T. And then solving for our temperature, our outlet temperature T, we can get that T naught, we'll get that T is equal to T naught plus XA times negative delta HR over R I CP I. And this one should look familiar. And again, this is kind of your expression for temperature based off of a adiabatic system that's at steady state where delta Cp is 0. So there is our energy balance. We can find sigma theta I CPI. So we have theta A CPA plus theta B, CPB plus theta I. Remember, we have an inert coming in too, CPI. It says that we only have A and I coming in, so theta B is 0. Theta A, always 1, and since it's 50% A, 50% I, theta I will also be 1. So we have CPA plus CPI, which, just plugging in the numbers that we have, CPA is 25, CPI is 75. That's going to give us 100 calories per mole Kelvin. Awesome. So there's our energy balance. And then we can kind of redo the mass balance. To be of the form. We still have that FA naught on the outside. Zero to XA, DXA. I guess KC prime plus K prime. Oh my god. Then our expression for CA, which we found up here, times CA naught, 1 minus XA, times T naught over T, dXA. We can pull out a handful of these values because they are constants. So FA naught, KC prime is not a function of temperature, and T naught obviously will remain constant, and CA naught we can also pull out. So that's going to give us our mass balance integral of the form KC prime plus K prime times T over K prime times 1 minus XA times DXA, where T is a function of conversion based off of the energy balance, which we just found. Put that down here. Ah, man, didn't want to move. Perfect. So now we've got a big-ish integral and a couple, technically two unknowns, because we don't, in order to find x, we have to find t at the same time. So we'll have to use ODE int to solve for it. And I'll show you guys how to do that. It's not too terrible. I'm hoping you guys are experts of this stuff by this point, but it doesn't hurt to show. So what I have in here right now, this is just all the constants. I've put them in the units that they need to be in. This KC, this is eventually what I solved for it to be. Because if you're a little confused where that's coming from, that's what we solved for in part A. Let me pull it up. Okay, so in order to do this, we'll have to define our function, and ultimately what we're looking for is W, and then X is also going to be changing. So let's put in first the function of temperature, or expression for temperature. And then I'll put in our expression for K, because remember that K is a function of temperature. Over T. And now our actual mass balance. I guess I'll write it in the way. So essentially what I did was rewrite it so that I have dw by dxa is equal to everything that I've got over here. T for kc prime times 1 minus xa. And that's what I'm going to plug in for my mass into the equation. That's actually what's going to be solved for. So I've got f a naught times t, 1t times k plus kc over k over kc over ca naught over t naught over 1 minus x, capital X. And then returning that, all right, so that sets up the function. And then we'll need a linspace for our conversions. So that goes from 0, and we want the answer to be at a conversion of 60%, so 0.6. And then W is just going to be equal to ODE int, my mass balance, my initial condition, which for a conversion of 0, which I guess is kind of my initial condition. That's the first thing it's going to solve for. So with a conversion of 0, we don't need any catalyst whatsoever, so that we'll set it to be 0, and then our linspace is xi. Okay, so if I did that right, it should give us our mass in grams. Yeah, it'll give us mass in grams. So if we take the last value, which is at 60%, which is what the one we care about, and divide that by 1,000, that should give us the mass in kilograms, if I did it right. Cool, 538. And he gives an approximate answer of 500. So that's pretty good then. So I hope that clears that up. Overall, this is you guys are on the downward slope of homework difficulty by this point. Excuse me. Really, this is the only one, this part's the only one that requires a lot of nonlinear solvers. So after this, it'll be more mass transfer, but for the most part, you guys have gotten through the hardest part. So this is a shorter homework, which is good. This one will still be due on Wednesday. And just let me know if you guys have any more questions on this. If not, I saw that someone had asked me to cover number 2, part C and D on the homework 7, which is due tonight. So that's probably what I'm going to do next, as long as there aren't any more questions on this homework. Okay. See if I can what I'm looking for. There we go. What was I looking for? Oh yeah, number 2. Okay. So let me pull up my Excel so I can troubleshoot. So it sounds like you said you were having issues with the your goal seek wasn't working too well. And you said if your goal seek wasn't, so you're asking about C and D. So then did you get a graph for part B then? Which one is it? Oh my god. Because if you did get a graph for part B, that's a good indicator that your solver is working, and it could just be that your guess is not quite correct. So one of these is wrong. I gotta figure out which one it is. It's this one. Okay, so I don't know if you're you said you're having trouble with the goal seek. I don't know if your solver's working, but I'll just show you kind of what I have set up in mine. So on this one, I kind of went over it before. We start with the mass balance and transition to the energy balance, and we remember that from the lecture that it's a steady state when your energy balance and your mass balance conversions are equal to one another. So from the energy balance, I got an expression for conversion, XA, right here. I plug this in to my expression for the the mass balance, which I got up here, which I got as this guy. Doesn't really work, that's fine. Oh, whatever, it's down here. So by plugging in my expression for XA into my mass balance, and then essentially going and setting all that to 0, and knowing that K is a function of temperature, along with X, actually, I can solve for my my conversions as well as my temperature. So that's what I did over here. So in here, it's just temperature. X was what I plugged in for X was my big long equation for the energy balance right there. And of course, it is a function of temperature. So it's taking temperature in. K was the Arrhenius equation, also a function of temperature. I'm using a different Arrhenius equation, but it works all the same. And then the mass balance, which is a function of tau, X, my conversion, and K, which these two, as we said, are functions of T. So and the way I have it set up is I essentially have this plugged in here, where I have tau minus XA over 1 minus XA times K. Setting that equal to 0 will give me the temperature I want. So by setting this guy equal to 0, it's going to solve for K, it's going to solve for X, and by solving for these, it's also going to solve for T to give me the value that I want. So that's just kind of a quick little crash course on how to do part A on number 2. So once I get this working, I've essentially just taken all of it and gone and plugged it in over here. So on this one right here, this is essentially, so this is my inlet temperature. These are my guesses that I'm not really sure of. Well, not really guesses at this point, I've actually solved for them, but these are the outlet temperatures at that inlet temperature. This is the conversion at that inlet temperature, my K, and then the mass balance, which is what I'm using to solve for it to set it equal to 0. So I can quickly show you, I guess, so this is essentially the graph for part B. Just ignore that gap, I was just trying something. This is a pretty good graph of what we are expecting on part B. On part C, let me open it because I don't remember. Okay, so suppose that you begin the feed with a feed temperature of 250 Kelvin, which you slowly increase. What inlet temperature must the reactor be heated before the reactor operates at high conversion? What are the corresponding temperature and conversion of the fluid in the CSTR just above this inlet temperature? So in this, so it says we're starting at 250 Kelvin on the inlet, and let's just pretend like we're down here and we're increasing, and it says at what point does it start operating at a high conversion? So if you'll look, ignore this one for now, don't look at that line. If you'll look at the upper one, you'll see that almost all of these are operating at a very, very high conversion, all of them pretty much over 90%. And after a while, it's just really just steadily approaching 1. And if you look at the lower one, all their conversions are about, 12% is the best we're getting, which isn't the best, which isn't very good. So what the problem is asking is, what's the inlet temperature that is going to give us, that's going to help us get up to this upper curve where we have these high conversions. And essentially that is the ignition point where we're going to all of a sudden start operating at, yes, higher, we're going to have a higher outlet temperature and a higher conversion as a result of that. And that point is going to occur essentially where this bottom curve will no longer have a solution. So I gave the hints in one of the other ones that the answer, for the inlet temperature, the answer is going to be between 400 and 425 Kelvin. So the best way of going about that is just kind of starting from 400. So if we start at, let's say 400, now we need to reset our guess. So we can probably still stick it. Let's go a little lower. Well, we already know the answer. Okay, so let's go to 401. And we'll say 337, because we know at 400, the answer, the outlet temperature is 336. So if we go and goal seek that, we're going to set that guy to 0 by changing that one. Get an answer. So let's go up a little bit more. Let's go up to, let's try 410. And, no, we want that to be 410. And then, I don't know, let's pick a temperature. Let's say 342. Sure. 342. So we're going to goal seek that to be 0. Okay, so I'm not getting a solution. So that tells me that 410 is too far, that is a temperature that is higher than what the ignition point is, and that the lower branch can't reach that. So we need to find we need to go lower than this to actually find a solution. So let's try 407. So we do that. I'm going to set that to 0 by changing that. Okay, still not solving. So, oh wait, no, I wanted that to be 407, sorry. And then this one should be 340. That to 0, changing him. Okay, still not solving. Let's go lower. Let's go to 404. That's a 404. Then we'll set that one to 340. Okay, same thing again. We're going to set him to 0 by changing him. Okay, I got a solution that time. Let's go a little higher. Let's try 405. And we'll leave that basically the way it is. And all right, and I see now I'm not getting a solution. So 404 works, 405 is too high. So that's a pretty good indicator that 404, or it's actually more like 404.9. It was approximately 405, but as we just saw, 405 will not solve. So if you get really close to 405, you could probably still get it. Oh, maybe not. Okay, well, I did it at 404 and it worked, so we'll probably just stick with that. So 404, as we can see there, that's how we get the extinction temperature, or ignition, sorry, not extinction. And then in part D, suppose that the inlet fluid flow, I guess in the rest of part C is asking what are the corresponding temperature and conversion of the fluid in the CSTR just above this inlet temperature. That if we go just slightly above this, we're going to obviously jump up to this upper branch. So basically it's asking we now know what the ignition temperature is. What is it going to be on the upper branch? What is my conversion and outlet temperature going to be? So that's why I solved for it on the upper branch as well. Okay, and then moving on to part D. Suppose that the fluid is now heated 5 degrees above the temperature in part C and is cooled by 20 degrees C where it remains. What will be the conversion? So our temperature we found in part C was, we'll say 404 for the fun of it. And then if we increase that by 5 degrees, looking at this graph, we're not going to be on this lower one anymore because we found what the maximum for this lower one was, what the ignition point was. So by increasing 5 degrees C, we are jumping all the way up here and we're going slightly higher. And now it says we're decreasing by 20 degrees. But when we decrease by 20 degrees, when we're on this, we're going to stay on this line because we need to get to the ignition point first before we can, extinction point before we can make any changes, before we can drop back down to the lower curve there. So essentially on part D, we have increased slightly past our ignition point to get us onto our outlet, onto our upper branch, and now we're decreasing by 20 degrees, but we will stay on the upper branch. So if we increase by 5, decrease by 20, that's going to put us at about 390. So that's kind of where I picked. So that's our inlet temperature. And now it's asking at 390, what is the conversion? And in order to get conversion, we have to get temperature because it's all related to temperature. So by increase, so we know we're at 390 for the inlet, and we know that we're on the upper branch. So now we need to solve for it on the upper branch. So we found that at 400 degrees, let me just delete that for now. We found that at 400 degrees, we had 382, for a 400 degree inlet on the upper branch, we had 382.79 degrees. So if we're going to want to decrease a little bit, and at 375, we find we're at 372. That's a 25 degree difference. So we will probably be a little closer to 382. So let's try 377 as a guess. Just kind of interpolating there. So same as before, we want him to be equal to 0, and we want to get it by changing that. So solve it, 379. And so that's our temperature, but what we're asked for on this one is the conversion. You get a conversion about 98.2%. I hope that makes it clear for part D. And then part E, what is the feed temperature which will cause extinction for this reaction system? Essentially, it's almost the same thing as part C, where with part C we were finding the highest possible temperature that the lower branch could go, or the ignition point, but now we're looking for the extinction point, which is the lowest temperature that this upper bound can go. So, and I gave you guys the hint that the temperature was going to be between 350 and 375 for the inlet temperature. So now you need to go and solve for what the outlet one will be. So a good guess, because I'm good at guessing, would be 363. Let's try that. So again, we're going to set that to 0 by changing him. There you go. So if you try going a little bit lower, let's try 362, maybe. We can leave that guess in. I think it should be fine. We want to solve for that to be 0 by changing him. Now we're seeing we're going to have issues. Oh, well, it dropped to 320. But if you see 320, that doesn't make sense for this upper branch. So that's actually dropped us back down to the lower branch. So that's a pretty good indicator that there isn't a solution for 362 on the upper branch. So let's try 363 at 360. 0. Changing that. Okay, doesn't look like it wants to solve. So let's go back up to 364. So once again, It's a lot of trial and error, guessing and checking. See, this one solved, and this number makes sense on this one. So we can also solve for a solution here. So this one would probably be about, let's try 320. Oops, I gotta drag all these guys up. There we go. So that's all. And then if I go and edit this a little bit, upper branch, edit. So there. Now you can see it starts to drop right there. It stays pretty linear, and then it just all of a sudden drops. And that's a pretty good indicator that we're on our extinction at that point. And then kind of the same thing, pretty linear, and then all of a sudden it starts to shoot up. Then that's our ignition point. So hope that clears that one up. I understand that was probably the hardest problem on that one. But you guys made it through. And for those who haven't done it yet, now you can see how to do it. So, right, covered homework 8 and a little bit of homework 7. Not sure if there are any more questions. I'll leave it open for a few minutes. If there aren't any, I will end the stream early, upload it, and I'll wish you guys a good week. Good weekend, actually. That's right, it's the weekend. All right, and again, if I don't get any questions for a few minutes, I'll probably just end the stream early and ask any questions you want. And of course, we're available through email. I'm thinking next Tuesday, I'm going to start using Zoom on Tuesday. I'll probably still do these Friday office hours through YouTube, but I'm thinking Tuesday I will do Zoom because I don't really see much of value in me going over the homework and recording it. So I think that's my plan. I'll just have to think about it. So yep, go ask any questions you guys might have. If not, I'll end it, and I wish you guys a happy weekend.